Hello everyone, and thanks for watching Edupedia World videos. In this video, we start our study of the dual character of light, namely wave-particle duality. So let's look at the meaning of a wave and particle first in detail. Waves are defined as a disturbance in energy without a disturbance in matter, or a propagation of energy without a transport of matter. For example, you could have transverse waves in which you put a disturbance on a rope and the disturbance would travel linearly. Another example of transverse waves would be a light wave in which the electric field and the magnetic field both change with time and space, but they are both perpendicular to the direction of propagation as well as perpendicular to each other. Waves exhibit phenomena like interference, and diffraction, which particles are not. Particles can be thought of as discrete packets of light. An example, an analogy that can make this clear to you was, let's say you have a field of grass and you want to water this field. So one way you can do it is you can have a pipe which just sprinkles water all over the grass. Then every portion of grass will get a small amount of water per unit area per unit time, and that area will keep on increasing uniformly as long as the pipe is supplying water. Another way to do it would be, you could just take small packets of water which contain a certain amount of water each, and you could just throw the packets on the grass. In that case, no piece of grass would continuously keep getting water and the amount of water increasing with time. Small portions of the grass, let's say this packet comes to this point and bursts, then this portion of grass will get a lot of water in an instant. Then maybe let's say this packet falls here and this portion of grass will get a lot of water in an instant. This is what we mean by discrete packets. This is continuous. You can break it down into smaller and smaller and smaller pieces, and smaller and smaller and smaller areas would get continuous uniform amounts of water. But in this case, there are discrete packets. An example which might illustrate this in terms of light, and this is actually seen in real life, is when you have a light of very small intensity and you put a light detector in a room. So let's say you have a very dark room in which you have light of incredibly small intensity. In that case, what would happen is, if you have a light detector, the wave quality of light would say that the detector would never detect anything, because you would need a certain amount of energy for the needle in the detector would move. However, that does not happen. What happens actually is, if you have a very dark room in which you shine a very small amount of light in a detector, periodically the detector will detect light, and it will detect light for an instant. It will detect light for an instant and then not detect for a long time. Then after a while it might detect another light for detect light for another instant. So that experiment demonstrates the particle nature of light, in which no matter how small the intensity of light gets, you don't have a very small amount of energy distributed all over space. You have a minimum amount of energy concentrated in small packets, and when one of those packets hits the detector goes off. Right? So that sort of proves the particle nature of light. Let's look historically at the different phenomena which caused physicists to believe light behaves one way or the other. The first phenomena would be the phenomena of reflection and refraction. That is the phenomena which you see first when you learn about light, primarily because you know that a prism can separate light into its aspects, which is due to refraction. So Newton was the first person who postulated a particle theory of light. He called what we now call photons corpuscles of light. And he maintained that these corpuscles are attracted by mediums such as water and glass, which is why light bends towards those surfaces. However, his theory was disproved because according to his theory, the speed of light would be greater in water and glass than it is in air, because the corpuscles of light would be attracted strongly by the glass and water. But by experiments we have seen that the speed of light in water or glass is much smaller than the speed of light in air. So that's why the particle theory was discarded. Now that does not necessarily mean everything in this particle theory was wrong. The simple aspect that he claimed, that light moves faster in mediums like water and glass, that aspect was disproved. At the same time, you had Huygens. By the way, both Newton and Huygens were able to explain Snell's law and the laws of reflection and refraction. Huygens used his wave theory of light to explain it, which we've already seen before, which uses the construction of wave fronts. Newton used the particle theory of light. Right. And Huygens assumed that the speed of light is different in different mediums. He didn't predict why that would be. Newton tried to explain it, but obviously the explanation fell short. So Huygens had his wave fronts, and he claimed that light is made up of waves which have wave fronts, and these wave fronts, when move into a different medium, move at a different speed, which causes a light beam to bend. Now, for a long time, scientists believed Newton's theory of a Huygens because of the respect Newton had in the physics community, because of his discoveries and explanation of gravitation, of the laws of motion, and so on. Then, in the late 1800s, in the late 1800s, Young did an experiment which we've seen before, YDSE, a Young's double slit experiment. He first started it with a single hole and then split into two holes, and that was the Young's double hole experiment. But the phenomena could be more easily shown if you had two slits instead of two holes. In that case, you would not have pinpoints, you would actually have bands of light. So with that phenomena, he was able to show interference. And nobody was able to explain interference assuming the particle theory of light. They did not have a real motivation to not believe Newton's theory, because the fact that light moves slower in water and glass was proved much later on. So they had faith in Newton's tellings, but once Young did his Young's double slit experiment and showed the existence of interference patterns, then we had to assume that light is made up of waves, because there was no possible way anyone could explain this by the particle theory of light. Also, at that time we started seeing phenomena like diffraction as well. Now these phenomena pretty much conclusively proved that light was a wave, because everything that could be explained by particles could be explained by waves, but there were these phenomena which could only be explained by assuming light was a wave. But then things changed near the late 1800s, very late 1800s, near 1900 or 1902, when we discovered the photoelectric effect. This was the subject of the last video, and we saw that there was no possible way to explain the photoelectric effect assuming the wave theory of light. Photoelectric effect could only be explained assuming that light has discrete particles called photons, and their energy is independent of the intensity. If you have a wave, then the energy in the wave is directly related to the intensity. The square of the energy is directly related to the intensity. However, for photons, we assume that every single photon has an energy which is independent of the intensity. The only thing that the intensity changes is the number of photons. And using that, we could explain what we saw in the previous lecture, that if you increase the intensity, the current changes, but the maximum kinetic energy or the stopping potential does not change. That only depends on the frequency or the wavelength of light. And this phenomena could not be explained by the wave theory at all. It could only be explained by the particle theory. So what we did was we assumed that light has dual nature, and that dual nature said that light sometimes behaves like waves, sometimes behave like particles. Now that might seem an unsatisfactory explanation, but the current reasoning is that light neither behaves like waves nor particles. It actually is what in advanced physics we call quantum mechanical. Now quantum mechanical is a separate thing. It's neither a wave or a particle, and we were really happy as physicists when we finally found out something which unified everything together. Just like there was a time when we thought electricity and magnetism were different, then we found out there were aspects of the same thing, electromagnetism. So you keep seeing these uniformities and convergence in physics all throughout, and the best evidence for this was when we found out that actually even electrons show interference and diffraction. When we found out that even electrons show interference and diffraction, that means if you take an electron beam and pass it through two slits, you will still see bands. That ultimately told us that all matter and photons, they're all quantum mechanical. There is no such thing as a wave, no such thing as a particle. Everything is quantum mechanical, but depending on the situation, what we see seems to behave to us like waves and seems to behave to us like particles in other situations. Waves and particles were defined by human beings. All matter, electrons, protons, neutrons, your desk, your monitor, they all are actually quantum mechanical. We'll not go into quantum mechanics, it's not in your course. All you need to know is quantum mechanics is only significant, it only shows significant results when you have very small sizes. So for you it doesn't matter whether your monitor is a wave or a particle, you would think it is made up of particles because it is too big to exhibit any wave-like behavior. Now another thing which supported the quantum mechanical nature of light was we discovered that even in interference and diffraction, it works even with just particles. So for example, if you did the Young's double slit experiment, and let me just draw the figure, I'm going to remove this all. You do Young's double slit experiment, and what you have generally there is a beam of light, and you initially might have a single slit, and the beam of light passes through that slit, and then by diffraction it makes wave fronts and passes here, and these two beams of light interfere and give us an interference pattern something like this. This would be the central maximum. Right, this should be smaller than this, I apologize. Yeah. But what happens when instead of a beam of light we send individual photons? Now if we just send a single photon, there is no reason for that photon to not go just straight ahead, right? If it's going from here and goes like here, it should go straight ahead. There is no reason for it to go somewhere else because it is not interacting with any other photons, right? So if we keep reducing the intensity of light to such an extent that you only send a single photon at a time, then most likely that photon will end up in the middle. Sometimes it might end up here, sometimes it might end up here. The greater the intensity, the more probability of finding the photon there. No intensity here means you'll never find the photon here. No intensity here means you'll never find the photon here. And that had to change our whole understanding of waves and particles, because this said that a single photon might sometimes go in the center, might sometimes go here, might sometimes go here, but never here and never here. And if you keep sending a single photon one at a time for years and years on end, eventually your graph would look like this. You would never have a photon in these dark regions, you would always have a photon in these bright regions. The brighter the region, the more probability that a photon will go there. And that cannot be explained by either the particle or the wave theory, and then we developed a new theory called quantum mechanics so that we can explain this. This is the most interesting result. Whenever you see wave phenomena, but you reduce the intensity of light so much that you only send one photon at a time, still you exhibit wave phenomena. That shows that it's neither waves because you can actually reduce the intensity to one photon at a time, but it's neither a particle because there's no reason a single particle would sometimes go here and sometimes go here, but never ever here. There is no reason for that to happen. So, and all of this could ultimately be explained by quantum mechanics. That's not really in your course. What you need to know for now is that everything, electrons, protons, neutrons, photons, everything is ultimately quantum mechanical, and the smaller the experiment size, the greater the wave properties, the higher the experiment size or dimension, the more prominent are the particle properties. Now a little bit of mathematics that is here. De-Broglee was the first to hypothesize that if photons show both wave and particle character, then electrons should show both wave and particle character. Before that we assumed that electrons were particles, but then he postulated that electrons should show wave character, and it has been proven. If you do the Young's double slit experiment with an electron beam instead of a light beam, electrons most likely go in the center or go in one of the maximas. They never go in the regions where you would, in case of light, observe dark fringes. So then the question became, for the wave character of light, we have related it to the particle character by saying the energy of a photon is h mu. How do we relate the particle character of an electron to the wave character? What is the wavelength of an electron? So he assumed the inverse of the relation we see for photons, and he just assumed that for a photon, if the momentum is h by lambda, then for an electron, the wavelength lambda should be h by p. And this simple result is called the De-Broglee relation, or the De-Broglee equation, and it tells us that if you have a particle, then this is the wavelength of that particle. Now h is very small. H is 6.626 into 10 to the power minus 34, So if you have, let's say, a 1 kg object moving at 1 meter per second, that means momentum is 1 unit, then this is the wavelength of light, which is incredibly small, and you would not be able to observe any wave character. We know that to see interference and diffraction, you need to have the slits of the dimension of that of the wavelength. So if the wavelength is 6.626 into 10 to the power minus 34 meters, this is the width of the slit you would need to have in order to see the Young's double slit experiment. And it's practically impossible to have a dimension this small. So that's why in real life we really don't see any wave properties of the particles. Any phenomenon, any object you see in real life will have a momentum that will be large enough, even if it is a small dust particle, the momentum will be large enough that the lambda due to this equation will be incredibly small. Even if the momentum is of the order of 10 to the power minus 10, then this would be 10 to the power minus 24. When the momentum becomes 10 to the power minus 30, 10 to the power minus 26, that's when you actually have 10 to the power minus 8, 10 to the power minus 9 here, and that's when you get the frequencies of light. Right. So this is the equation which relates the particle properties to the wave properties of any matter. There's a little bit of debate whether photons fall in the category of matter or not, so I'll just write any matter plus photons. That means whatever the momentum is, the lambda is determined directly from that momentum because h is a constant. So this concludes wave particle duality, where we've seen that every single object will show both wave and particle nature. However, the smaller the lambda, the more it will show the particle nature, and for any realistic objects of normal dimensions which you see every day, the lambda will be so small that you will never ever see their wave phenomena. Thank you.